Okay. So the most important thing now is joints. Okay, we're going to look at joints. And the joints, for this case, the joints the joints can either be glued, it can be bolted, it can be nailed, or it can be screwed together, right? Or any way you join. Okay, so when do you actually apply this analysis? Okay, when do you actually apply this analysis? So if we have a beam, okay, we have a beam. So this is my X, this is my Y. We have rotation about Z, and then we have our beam. So we have a beam over here. So now our beam is simply supported. Okay, we have a beam now. Hey, do apologize. So it's simply supported, right? And then for our beam, we're going to have over here is what we call spacing. I'll tell you more about this spacing later on. Okay, so there's a spacing of the screws or bolts, right? So why this spacing? Okay, so if we look at our cross section, right? So we maybe have evenly distributed load somewhere around here, for example. Okay, so if we look at our cross section now, right? So this is my Y, this is my Z, this is our rotation in the X. So if we have our cross section, so this is our cross sectional view. Okay. Right. So if we have our cross section that looks like this, so this is our cross section. So our structure look like this. Right. Then we make it more complicated. Typical me being a young engineer, make things complicated. So you see me drawing individual rectangular now. Okay. So the cross section is made this way, right? It can be wood, it can be steel, right? So I will have this, and then I decided to have, okay, so this is your cross section, and then I decided to put another piece at the bottom, over engineered, right? So you realize this is the cross section, by the way. Okay, so this is the cross section view. So on this cross section, right, I decided to, okay, I'm going to nail the side. I'm going to nail this side. And then on the vertical, okay, or on the intersection between the flange and the web over here, I'm going to glue. Right? Modern joining now, glue. Right? And then over here, I'm going to glue. And then I'm going to over design it. I'm going to put a nail. Okay. So this is nailed or bolted. Right? Over here, this is bolted. Plus glue. And this is going to be glue. Okay. So the cross section is made up of 1, 2, 3, 4, and 5 different members. They're either bolted or glued or bolted and glued together. Okay, now question for you. Where will the structure fail? Anyone? Where will the structure fail?
At the glued joint between 4 and 3.
Okay, you're right. The failure, okay, failure will occur at the joints. Okay, if we are on the street confronting someone on the street that is 3 times your size, right? Where are you going to hit him or her? Where? Right? Where are you going to hit the person? On the chest, right? Or on the what? On the what? Joint. Anyone? If no answer, I'm not being violent. I'm just giving you an example. You will hit at the what? At the joint. Because it's the joints that's going to be the what? Weakest. Am I right? The joints is going to be the part that is going to be the weakest. Okay. Likewise, if it's at the bottom part of your body, it's going to be your knees or your hip. Right? That's why you have hip replacement. You don't have rib cage replacement. You have hip replacement for that reason. Okay. Right. Now, so the failure will occur at the joints. Okay. If you have a section that is a cross section that's manufactured this way. Now you ask me, Eugene, why do you want to have a cross section measured done this way? It's for fabrication purposes. It's easier to what? Fabricate than make a cross section through a solid, through casting or through what? Welding. Okay. So for this case, we apply the longitudinal shear when we're going to calculate the stress we can calculate stress or strength of the joints. Okay. So what formula do we use? Okay, what formula do you use over there? So 2 formula. Right? So no, I'm not telling you the right. 2 formula and 1 formula extra that you don't need to really remember a lot is logic. Okay. So the shear flow, the key formula is the shear flow is equal to Q is equal to VQ over I. So this is the formula that we should be using. And if we look at the units for the shear flow, right? So this is Newton meter cube divided by 4. So the unit over here, if you cancel things out, you have Newton per meter. Okay, so that's the formula we're going to use. And does this formula look familiar? Yes or no? You seen it before? Anyone? Yeah, you seen it before last week. Right? So Q can be also equal to the force or the force that the joint could resist divided by the spacing of the screws or bolts. So that's why I put over here the spacing of the screws and bolts. And this analysis, in fact, I've done some consulting, okay, for landscapers, how to build a deck, and if the deck is under load, when will it fail, and what is the spacing of the what? Of the nail that they have to position, right? So this is one useful formula to apply, right? And then we know that the shear stress, right, is still the same, is also equal to VQ over IT. Okay, so three formulas as I mentioned, right? In fact, this formula that I'm drawing now is not really a formula. Okay, it's just, I wouldn't call it common sense. Is just the force that the joint could resist divided by the spacing of the bolt. And together, so you have these three formulas, and then I'm going to have over here, we're going to copy, and then I'm going to paste over here. And we are also going to apply to the same what? Same four rules. If we apply the same four rules, right? The rules did not change. The rules are still the same. And we are going to analyze a structure that has been glued together, the cross-section glued together, that has it can be a distributed load, gradient load, point load, whatever. Okay. Right. Okay. Any questions so far? So that's the theory part of it. Any questions, please? Anyone? No? Okay, let's do one example now. Okay, so this is going to be example number 2. So example number 2. Okay, so you guys will have this this image. So this is the question. Okay. And then I'm going to get the cross-section view, the longitudinal view, and the cross-section view. Right. So we have a double web. Griddle is construction from 2 plywood sheet. So when they say double web, you have an expression, you have an idea now. So this is the web, yes or no? So there's a left and a right, we call it a double web. It's construction from 2 plywood sheets that are secured to wood members at the top and the bottom, right? So this is the web is made of plywood sheets. And then we have the all these are the wood member. So they are made of wood, okay? So these are the wood member, right? At the top, at the bottom. So for this is pretty straightforward. Straightforward in what sense? That we know that the centroid is exactly over here. Okay, so that is our centroid. Then the normal stress. So the allowable bending stress for the wood. So given that under allowable bending is equal to 8 times 10 to the power 3 psi, and the allowable shear, okay, the allowable shear is equal to 3 ksi. And then we are also given that the spacing of the fastener spacing S is equal to 6 inches and each fastener can support or resist, okay, 600 pound in single shear configuration. Okay, so if you look at here, so each fastener can withstand 600 pounds. So force can withstand is equal to 600 in